Welcome back. We are in Chapter 4, Section 2. The title of this section is Optimization. In Section 4.1, we talked about finding minimums and maximums. Turns out that the largest and smallest value of a quantity often holds some sort of practical significance. So these are things that are important to us. For example, urban planners design traffic patterns to try to minimize delay. So there we'd be interested in a minimum. Such things belong to a field called optimization. So that's the inspiration for this section. Now, recall in section 4.1, we found local minima and local maxima, and local minima slash maxima tell us where a function is locally smallest slash largest. But now, what if we want to know where a function is absolutely smallest slash largest on a given domain? And there's a term for that. It's the global minimum and the global maximum, so very similar to the local minimum and local maximum. So that's our next definition. If P is a point in the domain of F, then what? Well, F has a global minimum at P if F of P is less than or equal to all values of F. So we call it a global minimum if it's less than or equal to all the other values. On the other hand, F has a global maximum at P if F of P is greater than or equal to all values of F. So, okay, well, we know we can find local minima and local maxima, but are we always able to find global minima and global maxima? So it turns out not always. So when do global extrema exist. And extrema, that's just kind of the catch-all word for a minimum or a maximum. So this next theorem tells us, it's able to answer our question. So this is theorem 4.2. It's called the extreme value theorem. And this theorem tells us if f is continuous on the closed interval a less than or equal to x less than or equal to b, then f has a global maximum and a global minimum on that interval. So if f is a continuous function on a closed interval, then f has a global max and a global min. Cool, now we know when it exists. How do we find them? So how do we find global extrema? Well, kind of depends on our function. For a continuous function f, on a closed interval from a to b, you do the following. First, you find the critical points of f on that interval. Next, you evaluate the function at the critical points and the end points. So we do that because it turns out, if a global max and a global min exist, they're going to be either at a critical point or at an end point. So those are the two possible places that they could be. So we evaluate our function there, and then we decide. So the largest value of the function tells us the global max, and the smallest value of the function tells us the global min. So take a function, evaluate it, take a function, find the critical points, evaluate the function at the critical points and at the endpoints, see what was the largest and smallest number that you found. We'll do an example of that to kind of put that together. So in this example, we want to find the global extrema of f of x equal to x cubed minus 3x squared plus 20 on the closed interval from -1 to 3. So first step, find the critical points. We already know how to do this, right? We practiced finding critical points in our homework from section 4.1. So to find a critical point, we first need a derivative. So f prime of x, that is 3x squared minus 6x, and that's it. So 3x squared minus 6x, take that, set it equal to 0. Then see, can we factor this? Turns out yes, we can. 3x times, this factors into 3x times x minus 2. Still set that equal to 0. So this tells us our critical points are x equal to 0 and x equal to 2. Okay, so we have critical points. Next thing is we need to get some function values. So evaluate f at critical points and endpoints. So we want to evaluate f at the critical points and the endpoints. Remember our critical points, 0 and 2. Our endpoints were -1 and 3. So let's evaluate. F of 0 is 0 cubed minus 3 times 0 squared plus 20. That gives us 20. F of 2 is 2 cubed minus 3 times 2 squared plus 20. That gives us 16. F of -1, -1 cubed minus 3 times -1 squared plus 20. That is also 16. F of 3, 3 cubed minus 3 times 3 squared plus 20. That gives us 20. Interesting thing. So I said, look for the largest number. That's going to tell us our global max. Look for the smallest number. That's going to tell us the global min. The smallest number is 16, and it happens twice. The largest number is 20, and it happens twice. That is okay. There's no rule that there has to be one global there's no rule that there has to be one x where the function reaches its global max. That's fine for there to be 2 or 3 or however many. So that tells us that we have a global minimum of 16 at x equal to -1 and x equal to 2. And we have a global maximum of 20 at x equal to 0 and x equal to 3. So that was a little weird. And when I chose this example, I didn't know that this is going to happen when I worked it out, but ended up keeping it because this does show an important thing is that you can have more than one location where the global min or global max is reached, so that if when you're working through this on the homework or on a test, you come across the situation, it is okay. It is okay. A little weird and not what we're expecting, but okay. Now this was for if the function was defined on a closed interval. Things are a little different if the function is defined on an open interval. If a function f is defined on an open interval or, which I'll show you that. So open interval would be a less than x less than b. So the endpoints are not included. So if f is defined on an open interval or on all real numbers, there may or may not be a global max or a global min. So open intervals aren't as friendly, so you might find that you may or may not have a global max or a global min in that situation. For example, here we'll just look at a picture. We won't, for now, we'll do an example. For now, we'll just look at a picture to kind of see what's going on. So start, here's my y-axis. Here is my x-axis. Let's make it colorful, since I can make things colorful. We'll say that's A, that's B. We want to draw our function. So there's our function. So where are some interesting points? There's one, there's one, there's one. And I'll label that capital A, capital B, and capital C. So at A, B, and C, at A we see a local min. At B we see a local max. And at C we see another local max, local min, but it turns out C isn't just a local min, it is a global min. So at point C, we are less than or equal to all other points on this graph. So why wasn't B a global max? Well, if you kind of follow the function here, so if we follow the function, we see that as you get closer and closer to B, it keeps increasing, and it would do this infinitely. So we never actually reach B, right, because the endpoints aren't included. But what we can do is keep getting infinitely closer to B, which means our function will keep getting larger. So we have a global min at C, but we have no global max. Can do another example of this. This time we'll actually use some numbers instead of just looking at the graph. So find the global maximum and minimum of g of x, I'll write that down there, of g of x, where g of x is 1 plus, sorry, I was thinking ahead to a different example. So find the global maximum and global minimum of g of x, where g of x is x cubed minus 9x squared minus 48x plus 52 on the interval -5 less than or equal to x less than infinity. Okay, so go ahead and pause this and try this on your own. So we worked through an example. This one's pretty similar, just now we have that infinity on the right. But besides that, process will be very similar to the first example. So go ahead and pause this, try it on your own, then see how you did compared to my answers. All right, welcome back. Let's see how you did. First step, find the critical points. And what is the first step in finding critical points? That is right, finding a derivative. So derivative is 3x squared minus 18x minus 48. So we take that, set it equal to 0, and solve for x. We see we can pull a 3 out here. So pulling a 3 out and factoring, we get it's 3 times x plus 2 times x minus 8 equal to 0. So that tells us x is equal to -2. Sorry. X is equal to -2, or x is equal to 8. So those are our critical points. Next, evaluate the function at the critical points. And endpoints. First up, f of -5. F of -5, that would be -5 cubed minus 9 times -5 squared minus 48 times -5 plus 52. And that gives us a -58. F of -2, -2 to the third minus 9 times -2 squared minus 48 times -2 plus 52. That gives us 104. F of 8, 8 cubed minus 9 times 8 squared minus 48 times 8 plus 52, -396. And f of infinity. So we don't know f of infinity, right? Or I guess g, actually, I've been putting f's this whole time, but our function was g of x. habit. Fix those. So G, G, G and G, in case you're wondering, where did the F come from? It was supposed to be a G. Yeah, okay. So, G of infinity, can't really evaluate that, 'cause you can't evaluate things in infinity, but you can think about it. So, the first thing here in G is an x cubed, so an infinity cubed is going to be really big. In other words, definitely bigger than 104. And as we keep getting closer and closer and closer to infinity, G is going to keep getting bigger and bigger and bigger, so we have no global max. But do we have a global min? Yeah, negative 396. So global min of negative 396 at x equal to 8 and no global maximum. And this actually lines up well with the photo that we drew, right? It had a global min, but it did not have a global max because the function just kept getting bigger and bigger and bigger. So we've got one last example. So the problem of finding the bounds of a function is closely related to finding maxima and minima. What do I mean by that? Well, first example, which is not really a real example, just kind of showing the point here. In example 1, on page 204 of your book, the value of f of x on the interval -5 to 12, and that's a closed interval. Remember, we talked about what these brackets mean. Ranges from -396 to 104. So we call -396 a lower bound and we call 104 an upper bound. So that's what we mean by finding bounds. We mean finding the lowest possible and highest possible values for our function. So now we will do one last example where we actually find some bounds. We want to find the best possible bounds for x plus sine of x for 0 less than or equal to x less than or equal to 2 pi. So on the closed interval from 0 to 2 pi. Well, we know that this means we're going to need to find the minima and maxima, and we know that mins and maxes happen at either the endpoints or the critical points. So first we need to find critical points. To find critical points, we need to take a derivative. So the derivative of x plus sine of x is equal to 1 plus the cosine of x. 1 plus cosine of x, set that equal to 0. That means cosine of x needs to be equal to -1. Where does that happen on the interval from 0 to 2 pi? Well, it turns out that happens when x is equal to pi. With these type of problems, it can be helpful to graph them and visualize them, not just for finding the answer necessarily. You kind of need to do that analytically, but to help you understand what's going on, it's really helpful to graph these. So I did that when I looked at this one. In terms of graph using what, you can graph using Maple, right? We've talked about how to do that. But if you don't want to deal with using the VPN to access Maple, totally fine. You're no longer required to do any Maple. Instead, there's Wolfram Alpha, there's something called ClassCalc, there is GeoGebra. If you Google graph a function of blah, usually it'll graph one. If you have a graphing calculator, that's fine. There are so many options out there of what you can graph something with. But I do really encourage you, pick one you like and start graphing these to kind of make sure that your answers make sense. Right, so I said cosine of x is equal to -1 at pi. If I graphed this and it was not, then I'd be like, ooh, maybe I need to go back and look at my math. So graphing can be helpful. Now, back on topic here. We have found a critical point. Now we're going to evaluate the function at the endpoints and the critical points. So evaluating at 0, we get 0 plus sine of 0, which is 0. At 2 pi, we get 2 pi plus sine of 2 pi, which is 2 pi. And at pi, we get pi plus sine of pi, which is pi. So this tells us our bounds are 0 to pi. Sorry, 0 to 2 pi. And you can write these a variety of ways. If you want to write them as a pair, that's okay as well, as long as you just indicate somehow you're going from 0 to 2 pi. That is the end of teaching a bunch of classes, making a bunch of videos, trying to remember what chapter we are in. This is the end of section 4.2. We will pick up in 4.3 next time. We're still going to be doing some optimization, but now we're going to be doing it with word problems. So we're adding an extra step.